The purpose of this podcast is to look more closely at the reciprocal function y equals 1 over x in the context of it being called a rational function, which deals with a so-called fractional form of a function. And at the same time that we'll take a look at the function itself as a rational function form, we'll also look to introduce the notion of limits for calculus, as well as connect this particular function form to transformations. So here is the so-called basic form f of x equals 1 over x that you see graphed in red here. And you can see the kind of behavior that this curve has. So it's classically introducing the notion of limits, because as x gets really, really big, right, as x tends towards positive infinity, then this number dividing into 1 just gets increasingly smaller. And that's why the y values, the so-called f of x values, basically head towards the y equals 0 line, which of course is the x-axis. So you end up introducing the beginnings of what is an asymptote, and in this case a horizontal asymptote. We can also let x tend towards negative infinity. Same kind of thing happens. Think about this number going to negative 100, negative 1,000, negative 1,000,000, negative 1,000,000,000. This fraction gets super, super tiny. It stays negative, of course, because you're dividing a negative number into positive 1. So you're approaching the y equals 0 from below. So hence, y equals 0 is emerging as a so-called horizontal asymptote. Or another way to start to describe the behavior of the curve is to say that this particular function has a limit towards 0, in this case y equals 0. You can also approach 0 itself. Of course, x cannot be 0 because division by 0 is not possible. So there's a problem here happening along the vertical plane x equals 0. But you can approach 0 either from 0's right or from 0's left. And so that's getting into some notation that if you're a higher level candidate, you'll need to be familiar with this left-right notation. SL, you don't need to worry about it. Just take in the flavor of what I'm trying to say. So if you approach 0 from 0's right, so think about numbers over here, like a tenth, a hundredth, a thousandth, a millionth. These are numbers getting super, super tiny. And if you divide those increasingly smaller numbers into 1, it blasts towards infinity, right? That's what is going on there. Similarly, if you come over on the other side and you've got these negative a tenth, negative a hundredth, negative a thousandth, negative a millionth, well, they divide into 1 lots and lots of times, but with a negative sign associated with the infinity factor, so they're going down towards that way. So you end up getting what is a vertical asymptote. So that's like the beginnings of a process that we can build on. So that's highlighted for you here. So the limit as x gets really, really big of this function would be what we just described. So as it's 1 over x, where x is getting tremendously large, so that ends up going towards 0. So this is kind of just a recap of what I was saying a few seconds ago. And as x approaches negative infinity, you can see that here, you get 1 over increasingly, well, big or small, depending upon your perspective, of these negative numbers. That also tends towards 0, so that horizontal asymptote at y equals 0 is confirmed. That's what's going on there. And you can have these two directions, like we said. This kind of approaching 0 from 0's right, approaching 0 from 0's left is not something at the SL level you need to worry about. It's just here to communicate to you what would happen if you do approach from this side. You blast, like I said, towards infinity. And if you approach from the other side of 0, you're going towards negative infinity. All right, so we've just confirmed those values there. So let's look at an illustration and really pull it apart. So let's talk about translating this particular curve 2 units to the right and 3 units up. IB could use what ends up looking like vector notation. So if you see this, it really is x, y. And so this is trying to say x goes 2 units to the right and y goes 3 units positive up. So basically, we're trying to come up with a new function, let's call it g of x, that's going to be f of x minus 2 plus 3. Not sure if you've seen that kind of notation yet, but that's basically saying evaluate the function at x of x minus 2. So when you plug in x minus 2 here, you get this piece of it, and add 3 to it. So this is trying to characterize a function, namely g of x, that ends up taking the original function and shifts it 2 units to the right and 3 units up. So what would we expect there? Well, graphically, what we have here for you dotted in red is the original y over x curve, and all we've done is shift it 2 units to the right and 3 units up. So if you look closely at the blue curve, which really is our g of x curve, all we've done again is shift 2 units to the right. So the problem at x equals 0 is now a problem at x equals 2, and we've taken something that had a horizontal asymptote at y equals 0, and it now appears to be a horizontal asymptote up here at y equals 3. Let's look more closely at what's going on here. So again, this is our new g of x function, and if you were to let x get really, really, really big, what I say to my students often is, think about Bill Gates and the amount of money that he has, which is heading towards millions, hundreds of millions, billions of dollars. That's how big it's getting. Take $2 away from it, or steal $2 out of his pocket or his wallet. He's not going to notice. So basically, this is just really the same kind of behavior as 1 over x. Basically, that gets so tremendously large, it divides into 1. Basically, it becomes 0. So approximately 0, which is what this piece tends towards, plus 3 ends up giving you that as x gets really, really big, so we're out here where x is getting really, really big, looks like y is tending towards 3. Go on the other side, same thing. You're just talking about negative a million, negative 10 million, negative a billion. Take 2 away from it, who cares? Basically, it's just 1 over this tremendously large number, which again goes towards 0, and 0 plus 3 is 3. So you're having this tendency towards the y equals 3 line as x tends towards positive infinity or towards negative infinity. This is definitely higher level type notation down here. So as you approach 2, you can approach 2 from 2's right. And as you approach 2 from 2's right, what happens here? You're talking about 2.0000-ish, 2.0001-ish kind of here. That difference is so tiny, but it stays positive. And that tiny difference, because x is getting desperately close to 2, that difference goes into 1 lots and lots and lots of times. So this is approximately 0 down here because the difference is so tiny. And it divides into a fixed number like 1, really an infinite number of times. And infinity plus 3 is basically infinity. So that's why the graph, as you get closer and closer and closer to 2 here, from 2's right, this blue graph is exploding towards positive infinity. Similarly, as you approach x equals 2 from 2's left, now you're on the 1.99999 side, and that difference of 1.9999-ish minus 2 is also super small, right? Getting small towards 0. But now that difference is going to be negative, and so that's why this is exploding then towards negative infinity, and negative infinity plus 3 is still negative infinity, and that's why it drops down that way. So let's take a closer look at the exact same curve, but IB likes to use this kind of representation for a so-called rational function, and then there's something about vertical asymptotes that are dependent upon, in this case, D and C, and the horizontal asymptote upon A and C. So let's look more closely at that. So again, we have, this was our curve, same one that we've been looking at. If you combine the actual fractions here, of course, multiplying top and bottom by x minus 2, so you have a common denominator. And so now here's our common denominator of x minus 2, and of course 3x is what's here, and 1 minus 6, where I come from, is negative 5. So now we have g of x in this altered form, right, that IB likes to build on just more generally. So let's take a closer look at what's happening here. So the question is, looking at g of x, which was this function earlier, we're going to analyze it now in this form, which matches this guy, just to be clear. Do all components of this graph, make sense? First of all, if you throw this into your GDC, you're welcome to do that. It should look like this. So let's explore it a bit more specifically and finalize our discussion here. So here's the curve, and it's supposed to have something to do with A, B, C, and D. And so the vertical asymptote is supposed to be at x equals negative d over c. Well, that would be the negative of our d, which is negative 2, over our c, which is hiding in there as 1, and boom, x equals 2 falls out and checks as our vertical asymptote. Horizontal asymptote is supposed to be at y is equal to a over c, and that looks like it just wants to be 3 over 1, and boom, there it is. That checks out as y equals 3. And if you take a look at this kind of analysis that we did earlier by using this other form, well, as x gets tremendously large, well, this is the idea of these two values here in x are getting so big. Who cares if you're subtracting 5 or subtracting 2? That's the Bill Gates thing. Nobody really cares. So the whole effect of this fraction really heads towards this ratio, because subtracting 5 and 2 do not matter when it comes to these values getting so tremendously large, right? So that ends up just going to the ratio 3x over x, where I come from, that divides out to be 3. And that's why we end up confirming that we have this y equals 3 asymptote. And then what about as you approach 2? Well, approaching 2 up top gives you darn near 6. 6 minus 5 is basically 1. Approaching 2 down bottom, where you have to look more carefully at both sides of 2, and you should be able to confirm, like we reasoned earlier, that that ends up going to positive and negative infinity, which is why we're going towards positive infinity here, and negative infinity in this direction. Also worth noting, and almost always worth noting, are your so-called y-intercepts and x-intercepts, right? G of 0 ends up just being, when you plug it in, 5 halves, boom, 2.5. There she is right there, 2.5-ish. When x is 0, that's y. And then if you set the y values equal to 0 to come up with where it crosses the x-axis, it looks like it wants to be somewhere between 1 and 2. And of course, all you have to worry about is solving the numerator there, and where that numerator becomes 0 is where the overall fraction becomes 0. And that ends up looking like 5/3, and that confirms for us 2.67-ish right there. Okay, that's pretty much it, and thank you.